This exam is a request. Again, if you've got any requests that you want me to go through, any exams you want me to do, send them through. So this exam is NZQA NCEA 91526 at level 3, and it's level 3 physics 2023, demonstrate understanding of electrical systems. So for this one, I'm going to be using the copy that's online. I'm going to be using the most common calculator that students in New Zealand use, and I'm also going to be using, as much as I can, the formula sheet that they give you. There are a couple of things on here that are missing or could be done a bit better, but we'll go with what they give us. Okay, so with that, let's do it to it. This exam I have gone through with a student, so I'm not going to be sort of looking at it first time, unlike the other exams that I look at. So we've got Kate is learning about capacitors, good for her. She investigates a capacitor found on a camera, good for her. The capacitor is labelled 185 nanofarads, which they give us as 1.85 times 10 to the negative 7 farads. This is kind of odd. Why would they give it a 185 nanofarads and then this on a different scale? But okay, we'll go with that. So that's the capacitance. The camera also contains a single 1.5 volt AA battery. So the AA battery tells us that this is a DC current, and it tells us that the voltage coming out of there is 1.50 volts. So far, so good. So, side note with these NCEA physics papers, they do put a lot of information into the questions. So it really does behoove you to go through and extract the information from those questions. There's a lot of clues there that they give you. Okay, show that the energy stored by the capacitor when it is fully charged by connecting to the battery is 2.08 times 10 to the negative 7 joules. So what have we got and what are we looking for? Well, we're looking for the amount of energy that's on this capacitor. Or maybe I'll put like a little C there. And we know that there is something to do with capacitors given as that. So the charge that's on the capacitor times the voltage. The problem here is that they don't give us the charge, but we do know from another of the formula that Q equals CV. So we can combine this algebraically from here, and now it's really just a matter of algebra. So the charge is the amount of energy that's on there is going to be half times CV times V, which is half CV squared. So 0.5 times the capacitance, which is 1.85 times 10 to the negative 7 times 1.5 squared. And we would grab our calculator and find that. Okay, so 0.5 times 1.85 to the power of negative 7 times 1.5 squared. And that gives us 2.08125 times to the power of negative 7. So 2.08125 times 10 to the negative 7. And they want us to show that it's 2.08. Well, that is 2.08, and it's 2.08 times 10 to the negative 7 for 3 significant figures, which is what they're really looking for. So that's how you'd answer that question. The next question is a little bit tricky. The reason it's tricky is because they're playing around a little bit with the units. So they give you the capacitor here at 185 nanofarads, and nanofarad is 1 billionth of a farad. But we know that it's 1.85 times 10 to the negative 7 farads, which is the same as what they've given you here, 10 to the negative 9 farads. They want you to find the charge, and the charge is in coulombs, but it's 10 to the negative 8 coulombs, so we're going to need to work that out if we don't have it already. And along here they want it in time in seconds, and if you can't read that, it's 10 to the negative 8 seconds. So a very, very, very short period of time for this capacitor to charge up. So the first thing we need to do with any capacitor when we're wanting to find the time is we need to find what the tau is. So the tau is given to us in the formula sheet as the total resistance times the capacitance of that capacitor. And we've got the diagram here, and the diagram tells us that the circuit used to charge the capacitor has a resistance of 0.270 ohms. Assume the rest of the circuit has no resistance. So in real life, if you're dealing with something as small as this type of capacitance, you'd want to at least fudge those numbers if you were an electrician or in electronics. But for us, we're going to assume that all of this circuit, everything that's outside this dotted line, this dotted box here, is going to have no resistance. So our total resistance is going to be 0.27 ohms. So 0.27 ohms is 10 to the power of 0, it's just as it is, times the capacitance, which is 10 to the power of negative 7 times 1.85. So this is negative 7, and this is negative 1. So when we do these, it is going to be on that negative 8 scale. That's why I put the negative 7 up here. So this is going to be equal to 2.7 times 10 to the power of negative 1 times 10 to the negative 7 times 1.85. So negative 1 plus negative 7 is going to be negative 8. So it's going to be in the scale that we want. So let's find out what that is. And notice here that the main lines are 5 times 10 to the negative 8, 10, 15, 20, 25. Okay, but it's given to us in time, not in tau units. So 0.27 times 1.85 to the power of negative 7. And that's going to give us 4.995 times 10 to the power of negative 8, which is going to be 5.0 times 10 to the power of negative 8 when we have three significant figures anyway. I mean, if you want to quibble about 5 nanoseconds, that's fine, but if we're just dealing in a different scale here, so that's going to be good. So that tells us that each of these time units here is going to represent 1 tau. So we could even rewrite that tau, and this would be 2 tau, 3 tau. It just works out that way. Okay, what unit do we use for charge? We use coulombs. So now we need to work out what the actual charge is going to be at any given moment in time. In order to do that, though, we need to work out what Q max is. So Q max is what the capacitor would hold if we charge it for infinity. So we're going to just use the regular old charge on a capacitor formula. So the capacitance is known. We know that the capacitance is 1.85 times 10 to the negative 7 farads, and we know that the voltage is 1.5 volts. And hopefully when we multiply these together, we're going to get something in the terms of Coulomb to the power of negative 8. So let's multiply them together. So 1.85 times 10 to the negative 7 times 1.5, and that's going to be some number. Grab our calculators. So 1.85 times 10 to the power of negative 7 times 1.5. 2.775 times 2 to the power of negative 7. So I'm going to move this decimal point to the right to make it in terms of negative 8 units. So that's going to be 27 point times 10 to the negative 8 coulombs, which is the units that we've got there. So it's going to be, so what are these? 1, 2, 3, 4, 5. So these are going to be 2, 22, 24, 25, 27. So around about there somewhere is going to be our maximum, our Q max. So the capacitor will never have a charge greater than that. And now for this, we're going to apply the formula, and there's a few ways of doing it. You can remember the percentages. I always remember it in these terms here. It's going to be Q max 1 minus E to the negative T over tau. If you remember that one, you'll be good. But remember, in our scale here, each one of these lines here is 1 tau. So I'm going to work it out in terms of tau. So Q max is going to be, so Q as a function of tau in this case, because T in this case equals tau, the lines anyway, 1 minus E to the negative tau. And I'm just going to put it on pause, and I'm going to work all those out and come back to you. I guess first off, we can do Q0. So that's going to be, Q0 is going to be 27.75 times 10 to the negative 8 times 1 minus E to the negative 0. 1 minus anything to the power of 0 is 1. So 1 minus 1. So this is going to equal 0. So anything times 0 is 0. So that shouldn't really be all that shocking. Before we put any charge onto the capacitor, it has no charge, which is kind of self-explanatory. Let's do the first one just for 1 tau. So that's going to be 27.75 times 10 to the negative 8, 1 minus E to the negative 1. Let's put that in our calculator. So 27.7 times 10 to the power of negative 8, brackets 1 minus E to the power of negative 1. And then we want to close brackets. So 1.75, 413 to the power of negative 7. So we're going to move across one. So it's going to be 17.5. 17.54 times 10 to the negative 8. And then for the next ones, I'm going to do them off camera. Okay, so I've done all of those now. Put them in the calculator and found the answer. And you see they get closer and closer to this 27.75 number. So when we first start off, it shoots up from 0 to 17 and then very, very quickly gets closer there. So you should expect it to be asymptotic exponential growth, and it's going to be asymptotic to Q max. That's what we expect. So let's test to see whether it actually does that. So the first one is when tau is 0. And remember, I can get away with doing that because I relabeled this as tau, because we knew that tau is approximately 5 times 10 to the negative 8 seconds. So 5 times 10 to the negative 8 seconds is 1 tau. And 10 to the negative 8 seconds is equivalent to 2 tau. So we could do that in this case. So the first one is going to be 0. There's no charge. The first after 1 tau is going to be 17.5. So that's what, about here somewhere. The second one is 23.99. So 20 is about here somewhere. The third one, 3 tau, is going to be 26.37. So it's pretty close up here. And then the next one's going to be almost imperceptibly close to that asymptote. So it's going to have that shape. And that's that question. The next one's a really, really nice question. So we're told that a charged capacitor can be discharged through a lamp by pressing a switch. In the camera, the lamp flashes when a picture is taken. Hopefully you all know how a camera works. So here we have our capacitor, and here we have a light. Now the thing to realize about that light is it is essentially a resistor. Okay, so Kate fully charges the capacitor with her 1.5 volt battery. So in other words, on this capacitor now we have Q max that we already worked out, and that was 2.775 times 10 to the negative 7 coulomb. The resistor, we're not told how powerful the resistor is. Okay, but we're told that she goes into the camera and she finds that she has wires in the capacitor that allow the capacitor to be charged to 200 volts. So they kind of sidestep what it is here. There is an electronic component that's not covered in NCEA 3, which allows you to do that, to step up the voltage. So explain how this arrangement allows for a more powerful flash. In your answer, you should show how the energy stored at the 200 volt compares to the 1.5 volt, and the higher voltage increases the initial current from the capacitor when it is connected to the bulb, how the brightness of flash will be affected by higher voltage. Okay, so one thing to note is that in this capacitor, the only thing that's changed is the voltage. So we have voltage is 200 volts versus, notice the amount in the resistor is not changed, and they don't even give us a value for the resistor. That tells us that the tau is RC, and the capacitance is also not changed. The resistance is not changed. So the tau, the rate at which the capacitor will discharge its charge, will be the same for both. So if we have a higher initial current and a higher amount of energy on these different capacitors, then all of that energy must be released at the same rate, but it's not a linear amount. It's just most of it goes immediately, then a bit of it, and most of something else goes immediately, and then a little bit of it. So the way it's going to look is, here we have our 1.5 volt capacitor, and here we have our 200 volt capacitor. The shape of these curves is going to be the same. There's just going to be a big gap in the amount of charge that's carried, the amount of energy really that's going to be put out by these capacitors. Okay, let's work it out then. So we don't know what tau is, but we know that tau is the same for both. So the amount of energy that is stored in a capacitor is known to be half CV squared. We already worked that out. And we already worked out the amount of energy in 1.5 volt capacitor. We worked out that it was 2.08 times 10 to the negative 7 joules. We worked that out in question 1. So let's work out the amount of energy that's stored in a 200 volt capacitor. So it's going to be half times the capacitance, and that's 1.85 times 10 to the negative 7. I know they give it to you up here, but I'm going to keep it in this form, times 200 squared. And we can see here that it's not even going to be close. So we would grab our calculator. So 0.5 times 1.85 to the power of negative 7 times 200 squared. So it's going to be 40,000. 3.7 times 10 to the power of negative 3. So 3.7 times 10 to the power of negative 3 is many times greater than 0.08 times 10 to the power of negative 7. How many times greater? I'm not too sure, but a lot. I think I worked it out when I first did it, and it's about 18,000 times more energy is going to be in this, in the capacitor, when we have it done in that way. Okay, but they then ask us to have a look at the initial current from the capacitor when it is connected to the bulb. So for this one, we're going to go to Ohm's law, and we're going to kind of rewrite it. My pen will work. So we know that Ohm's law is that, and we're going to say this is the initial current, and we know that the total of the resistance is not going to change. The total voltage is not going to change. The voltage is going to be set by us, I should say. So 5 is going to be equal to whatever the initial current is times the resistance. So the current is going to be 1.5 divided by R. So the voltage, let's just put it in this terms first. It's going to be the voltage divided by R. Remember the voltage is 1.5. It's going to be the same for both of those. The fact that the initial current for one of them is going to be different is going to be because of this voltage. And hopefully you should know that a current which is equal to 200 divided by R is much greater than the initial current 1.5 divided by R if R is the same number. 100 over R is much greater than 1.5 over R. Perhaps that's a better way of putting it. Many times greater, whatever 200 divided by 1.5 is. So what? More than 100 times greater, which means all of it's coming out at the same rate. Remember, the tau is the same, so that's going to be good for us. So next we're asked, how is the brightness of the flash affected by the higher voltage? Really, when we say the brightness, we're really talking about the power of this. And if you remember, power is IV, IR. So this, we can rewrite this, the power as the voltage squared divided by the resistance. And if the resistance is the same, then 200 squared over the resistance, we know that's going to be way more than 1.5 squared over that same resistance. So the power that's going to be put out in this, from this capacitor through this swanky wiring system that they've got, is going to be almost non-comparable. Right. Question 2, transformers and inductors. Kate's school has a demonstration transformer pictured alongside, so I guess you're just going to have to use your imagination. She connects the 12,000 term primary coil, red in the picture. All right, so there's a coil that goes, a red coil, so that has 12,000 turnings, to a mains supply which is 240 volts RMS. The RMSs are kind of important, but kind of not important. The RMS tells you that this is an AC circuit. Okay, to the main supply. She connects an AC voltmeter to the blue coil. So there's a blue coil apparently that goes around there like that. And coils. Calculate the RMS voltage. So if one is an RMS, the other one will be an RMS as well, from the 600 turn secondary coil. Okay, so what are we going to use for this? We're dealing with transformers, so the key equation for this is going to be the voltage in the secondary divided by the voltage in the primary is equal to the number of turns in the secondary to the number of turns in the primary. And we want to solve for Vs. So Vs is going to be in as the amount of voltage in the primary times the number of turns in the secondary divided by the number of turns in the primary. And we know 1,000 and we get a number. So let's grab our calculator. So 240 times 600 is 444,000, and we divide that by 12,000. Okay, so I can see what's going to happen here, and that's going to be 12. So it's going to be 12 what? It's going to be 12 volts. And that's it. That's how that's done. So now we're told that the two coils are held by a ring of laminated soft iron. So in other words, we put a ferromagnetic core in it, which runs through the core of each coil. Explain why an AC voltage in the red coil, that's the primary coil, produces an AC voltage in the blue secondary coil, and why the coils are wrapped in an iron ring to begin with. And it's a pretty good question. So the reason that we have that a transformer only really works in an AC circuit is because the alternating current, by definition, is always changing. So essentially, a coil is just an inductor. When we put a current through it, it's going to create a magnetic field. B is the letter we use for a magnetic field. But the fact that it's always changing means that this field is constantly growing and collapsing, growing and collapsing, growing and collapsing. And that creates a magnetic flux which goes through the other coil. And then Lenz's law says that in order to oppose that, the secondary coil will create current to oppose that and a magnetic field. Okay, so it's in reaction to the first coil, the second coil is also going to make a magnetic field that opposes that and a current that opposes that as well. And it's going to be on the same frequency as the first one. So remember, Faraday's law says the induction is it's going to be proportional to the change in the flux. So the flux will change, and because of Lenz's law opposing that, it's going to create an output. It's going to induce. So we're really combining Lenz's law and Faraday's law of induction. Quite a brilliant invention, actually. So the reason that it is an alternating current is because it's collapsing and growing. The induced current and magnetic field will also be collapsing and growing in an AC circuit. In fact, it's in an AC current because pretty much because it has to. There's no other way that it can do it. It's not going to be out of phase. They're both pretty much joined at the hips. The second question is, why do we have the core? So a transformer will quite often look like this. So that's the primary coil. There will be sort of a secondary coil, and then there will be sort of this ferromagnetic core that goes through both of them. And the reason that's there is it makes the transformer really, really more efficient, more powerful and more efficient, really. Because remember, we have essentially two inductors joined, and they're joined by a magnetic field. And the iron core acts kind of as a medium, really, for that magnetic field. So it's almost a wire that connects the magnetic field in this inductor to the magnetic field in this inductor, it means that the magnetic field can almost flow through this ferromagnetic core. So the reason that we choose iron because it is quite easy to magnetize. And what happens when we put a magnetic field through it, all of the little dipoles, that is little magnets that are in the iron, will align when we put a magnetic field through it. So it is going to work as a really, really good medium, a really, really good conduit of magnetic field. And it increases the efficiency of an inductor and thereby and the efficiency of a transformer by a lot, like multiple times more efficient. It's much more efficient to run magnetic field through this core than through open air. And when there's more magnetic field going through it, there's more flux. More flux means more induced current. The next question tells us that Kate connects the 12,000 turn primary coil in a circuit with a 12-volt battery DC and a 12-volt car headlamp bulb. The cores and the coils are still linked with iron. Explain why the headlamp bulb only comes on after a slight delay. Okay, so for this, we really need to look at Lenz's law again. And Lenz's law says that the inductor will resist, and I put the in resist because we really say that it impedes the build-up of charge slash the magnetic field that's induced, because it wants to oppose change. Okay, and the reason it's the way it's going to do that, it's going to create a back EMF, electromotive force, that opposes surge in current. Okay, so it's going to take a wee while for it to build up that magnetic field as well. So it's going to build up that magnetic field, and then but when we turn it on, it's going to resist that. And it's not going to go sort of literally go with the flow until that magnetic field has been produced. And then it would resist taking that charge off. So, I mean, it's going to be pretty quick. When they say a slight delay, it's going to be pretty quick delay. We're going to put it in, we're going to put the current into this current, and then this magnetic field is going to build up to resist that and creates a back EMF before current is induced through that inductor. So Lenz's law explains that. So your answer should have reference to Lenz's law and back EMF, and the fact that it wants to resist the initial change in voltage from 0 to 2. The next question says that the power supply that supplies Kate's area is 50 kilowatts of power, so 50,000 watts of power. And the transmission line near Kate's house carries 50 kilowatts, which is the same, of power to an industrial user. The voltage across the transmission line is 220 kilovolts, so 220,000 volts. The resistance of the transmission line is 4 ohms for every kilometer. Calculate the power loss as heat energy across the distance of 300 kilometers. Comment whether this amount calculated is significant compared to the situation where the voltage is not stepped up to 220 kilowatts, but is transmitted at 25 kilowatts. Okay, interesting question. So let's pull out what we've got. So the power the initial, well, I'm going to say the initial power here that we start with is going to be 50,000 watts. I'm going to put a little line over the W there so you can see that it's watts. Transition, that's the same. The voltage across the transmission line, so the voltage is 220, and the resistance, so the total resistance is going to be 4 ohms times 300 kilometers, which is going to be 1200 ohms in total. Okay, heat energy lost. So we're going to be some point looking at energy in terms of joules. Okay, so there's our total resistance. So let's look at the amount of current that's going through this line over the 400 kilometers. And that's going to be equal to the power over the voltage. This comes from power equals IV in your exam formula sheet. So that's going to be 50,000 watts divided by the voltage, which is 220,000 volts. And I don't know what that is off the top of my head. Let's use our calculator. 50 divided by 22123 amps, which is not much. That's pretty good, and it's one of the reasons why we transport electricity through very, very high voltage. It has a very, very low current that we need, and it loses not much energy as well. It's really, really efficient way of transporting electricity. So then we need to work out the power loss. Well, the power loss, we're going to be able to work that out by, how are we going to work that out? We are going to need to combine a couple of things. So P equals IV and V equals IR. So P equals IV. So P is going to be equal to I times IR, which is going to be I squared R. So that's going to be 0.227 square times the resistance, which is 1200 ohms, which is going to be a pretty small number. Grab our calculator. 0.227 squared times 1200. 61.8 watts. So that's the amount of power that we're going to lose. How much energy is that going to be? Well, we don't really care. We can't really work that out. The power lost as heat energy. So that's the power we've lost. So remember, power is energy divided by time. We don't know how much time it's going to take to get there, so we can't work it out, but we can work out the amount of watts that are lost. Now we're on to question 3. Kate builds a circuit with a single signal generator set at 200 hertz, an AC ammeter. So here we have our 200 hertz AC circuit, and it's an AC ammeter, so we have our ammeter there, a 15 ohm lamp, and a capacitor with 1.2 microfarads. So 1.2 microfarads is equal to microfarads is 1.2 times 10 to the negative 6 farads in series. I don't think the series bit is going to matter too much. Show that the capacitive reactance XC is 663 ohms, and hence determine the impedance of the circuit. So we need to prove that it's this, and then determine the impedance of the circuit. Okay, the formula that we're going to use is going to be that one that's given in the exam. So it's 1 over 2 pi fc. So 1 over 2 pi, frequency is 200 times the capacitance times 1.2 times 10 to the negative 6. And now we grab our calculators. So 1 divided by, now we're the pi on these calculators, 2 pi times 200 times 1.2 to the power of negative 6 is 663.1455962, which is 663.023 significant figures. So there we go. So ohms. So what are we going to be looking for now? We're looking for the total impedance. And the total impedance is Z. Now this is one that they don't give you. You can work it out using what's given to you, but if you're going to remember one, I'd remember this one here. So the total impedance is the total resistance squared plus the total impedance capacitant reactance squared. So that's going to be square root of the resistor is, what was the resistor? 15 squared plus 663 squared. We're going to go with that three significant figures number. So that number squared plus 15 squared is 43,439,987. And then I'm going to take the square root of that. So I'm going to raise that to the power of 0.5. So 663.13, which is pretty close to what we've got. So this most of the impedance is coming from this capacitor, really. Next, we're told that Kate increases the frequency of the signal generator from 200 hertz to 20 kilohertz, and then up again to 200. So she's making a big step here. So this is going to be 200 hertz. This is going to be 20,000 hertz. And this one is going to be 200,000 hertz. I give an in-depth explanation of what Kate will observe in the circuit at each frequency compared to her observation in A. In your answer, consider the effect of changing the frequency on the impedance of the circuit, the RMS of the current, the brightness of the lamp. All right, for all of these, let's look at all three of these things separately. Well, the impedance of the circuit we've already worked out is Z is the square root of R squared plus the impedance, capacitive impedance there. That's there. We worked that out at 200. If we put, you should see that if we start increasing this value, it's going to go up. This value here is going to go up. If we decrease it, this value is going to go down. But we also know previously that the total impedance from the capacitor is this. And because F here is downstairs, as F goes up, then the impedance from the capacitor, the capacitive impedance, must go down because it's an inverse relationship. So now when we do that, and of course the capacity of the capacitance is going to stay as it is, if we take it up to 200,000, okay, that's the frequency that we're going to use there, and the capacitance was, what was capacitance again? It was in like 1.2 times 10 to the negative 6. farads, it's going to be a really much smaller number. And in fact, let's work it out. So 1 divided by brackets 2 pi times 200,000, and we're going to have zeros, yes, times 1.2 to the power of -6, 0.663. So really small. So as the frequency goes up, that causes the reactive capacitance of the capacitor to go down, and that causes Z, the impedance, to go down. In fact, Z is going to go to the resistance. So eventually this one here is going to go to 0. Those of you who are doing calculus will know what I'm doing there. We're taking the limit. So what's going to happen to the RMS current? Well, from this, we know that as the frequency goes up, the Z must go down. And we know that Z is V equals IZ. So if we want to make I the subject, I is going to be the voltage, the RMS voltage, divided by Z. And the voltage stays the same. Z is getting smaller and smaller and smaller. And it's an inverse relationship. So therefore, as Z goes down, the current must go up. So what does this have? What effects does this have on the brightness of the lamp? Well, the power of the lamp is what we're really talking about. Is this? So this is the amount of energy or work done by the lamp in a time. Now remember, previously we worked that out, that the power is going to be equal to the current squared, and it's an RMS current, but we don't really worry too much about the fact that it's RMS, it's just the current, times the resistance. Well, the resistance is going to stay the same, so the change in the resistance is 0. The current, the change in the current is, it's going to be going up. So something going up squared means that the power must also go up, and the power is going to go up proportional to the change in the current going up squared. So it's going to go up quite a bit more as we up the frequency. All right, so now we're given the old resonant frequency question. Kate adds a 0.200 Henry inductor in series with the capacitor. So now we have a resistor, a capacitor, and an inductor in circuit. So you should be thinking, okay, now we have an RLC circuit. So now we can start working out resonant frequencies. And you should also know before we even start that the most current goes through when it's at its resonant frequency. So while the signal generator is set to 2000 hertz, the lamp is off. But in other words, there's no current going through, so it's not doing any work. But as she slowly decreases this frequency, the lamp suddenly glows brightly and then goes off at the lower frequencies. Okay, so that tells us that our resonant frequency must be somewhere between 0 and 2000 hertz. So our resonant frequency, F0, is going to be in there somewhere. So we're going to calculate the frequency at which the bulb glows brightest. Okay, well, we could do a lot of things, but let's just jump to the formula that's going to help us. So F subset 0, which is the resonant frequency, is 1 over 2 pi square root LC. The capacitance, it's given to us already, is 1.2 times 10 to the negative 6. The inductance is given to us as well. It's given to us as 0.20 Henry. So 1 over 2 pi times 1.2 times 10 to the negative 6 times 0.2. It's going to give us our resonant frequency. And I've no idea how to do that on the top of my head. So 1 divided by 2 pi times the square root of 1.2 times 10 to the power of negative 6 times 0.2, close brackets, 324 point, which sure enough is between 0 and 2000 hertz. So what's going to happen is that the capacitance and the impedance of the capacitor, and that's going to go towards 0. So they're going to cancel out. If you remember the formula, so the total impedance in an RLC circuit is the resistance squared plus, but if these two equal each other, then this goes to 0. So it's going to be equal to the square root of R squared, which is R by definition. So what's going to happen is as we increase in frequency, the impedance from those two appliances interacting with each other is going to go to 0 until it's at its maximum there, in which case there's the least impedance. So the only impedance is going to be from the resistor itself, the resistance. So that means that there's going to be maximum current, which means there's going to be maximum power and light going through this light bulb. In the last question, we're asked to explain how does the inductor affect the impedance of the circuit. So I've almost essentially done it here, and equals the resistance in the circuit. So for this, we know that the resonant frequency is where it's brightest, is when it's brightest. When it is brightest. So how come? Well, we know that when they're in a RLC circuit, the capacitor and the inductor are 180 degrees or pi radians out of phase. The reactance from the impedance from the inductor is 2 pi FL, and the reactance from the capacitor is 1 over something which is pretty similar, FC. So if we know that the total impedance, I should say, is R squared plus XL minus XC, because they're going to be cancelling each other, partially squared. So from this, you can actually combine those two together to find the resonant frequency. So I would, if you're interested in doing that, you can do that, but I'm not going to do it here. But we can see here that when XL equals XC, this term here equals 0. So therefore, as these come together, as we reach this point in time, given a different frequency, the impedance itself is going to be equal to the square root of R squared, which is R, because the impedance of the inductor and of the capacitor are going to be 180 degrees out of phase from each other, so they're going to cancel each other out completely at that point. So therefore, when we're at the point where we have resonant frequency, the resistance, all of the resistance is just going to be 15 ohms. That's it. We're not going to have anything greater than that. In fact, let's even work it out. Let's say that we set the frequency for our one here at, say, 10 hertz. How much resistance and how much impedance is going to be applied to the circuit? Well, we know the resistance is going to be 15 no matter what. The impedance from the inductor is going to be 2 pi frequency of the inductor, and that's, what was that set at? That was set at 0.2 Henry. So that's going to be 2 pi times 10 times 0.2 Henry. So that's going to be 10 pi ohms. And we know that the capacitance, the impedance of capacitance is going to be 1 over 2 pi frequency of the capacitor. The capacitor is given as, what was the capacitor again? Going all the way up here, 1.2. So that's going to be, I think we've already worked this out, times 10 times 1.2 times 10 to the negative 6. So 10 hertz, 1 divided by pi times 10 times 1.2 times 10 to the power of negative 6. A lot. 13,900 something. 13,262. So our total impedance when we're at 10 hertz is going to be square root of 15 squared plus this 10 pi ohms minus 13,262 ohms squared, which is going to be a lot. So we're going to have maximum impedance, and when we have maximum impedance, it means that the current is minimal. And when the current is minimal, because P equals I squared of V, the minimal current means that our power is also going to be minimal. So when the frequency does not equal the resonant frequency, XL minus XC squared does not equal 0. Z does not equal the resistance, and the resistance when Z equals the resistance was what we had when we had resonant frequency. So therefore our current must go down, and because of that, the power in the light bulb must also go down. And that's the exam.